Hello, my name is Liliana Reyes, and this is my Lab 1 Constant Velocity video lab report. For our first lab, we were asked to record an object moving at a constant velocity. We then placed the video in our tracker program and analyzed our video at its position at different times. We then created a computer model that would predict our position and time of our object. The next step was to add the two data and put them into a spreadsheet. Our objectives of this lab was to apply our Newton's second law to a real-world example, which would be at constant velocity. Now we will take a look at our video on tracker. So as you can see, we have an orange rolling across the table that is moving in the positive x direction. And as you can see, we also set the axis at the point where the time t is equal to 0 at the center of the mass. We also can see we have a positive axis, a positive slope, because we are moving in the positive x direction, and we also see our initial position, which is at, and also our video is running for 0.6 seconds. And if we were to perhaps switch the axis, we will see that we would be moving in the negative x direction, which will change the graph to have a negative slope, as you would see, would look more like that. Now we will take a look at our code. So our code, we are given a starter code, and so we first input our mass, which is 0.26 kilograms. Next, we have our position vector, which we can grab from our tracker program, and it is at where time t is equal to 0. And also we can get our velocity by looking at 2 points, and I chose to choose the first 2 points of the experimental data. Next, in our code, we're looking at our while loop, which will run for the duration of the video, which is 0.6 seconds. Next, we will set our fnet vector equal to 0. And next, we will apply the momentum principle to our code. So we have our initial ball velocity, and we're going to keep updating that throughout the duration of the while loop. And we will do fnet over the mass of the ball, which is ball.m, and times delta t. So we also update our position. We will start with our initial ball position, and we will update that by adding our ball velocity times delta t. And now we will run the code and see where our data takes us. So as you can see, it is moving in the positive x direction, and we also have a positive slope that is linear and constant. So now we will take a look at our Excel sheet, which compares both of the graphs. So as you can see, we have our model position and our red line, and we have our experimental position by blue squares. So as you can see, they're both linear, and although the squares are skewed off a bit, I feel like it has a lot to do with the way the orange was moving at the end. It started to move more in the different direction as it rolled off the table, which I feel had something to do in the difference. But overall, they are both linear. They're both moving in the positive x direction, and they're both positive slope, and both have a constant velocity. And from this, we can see that because we have a zero net force acting on our orange, we can implement Newton's second law here, which states because we have that zero net force, we will also have a constant velocity. That constant velocity is shown by our slope, that is constant, and just our linear line in general. Also, it is not possible to say how many pushes and pulls are added together to give the zero net force, because we are not giving the information. All we know is the initial position of the orange, but other than that, we cannot conclude on why we have assigned the zero net force.